purpose of this lecture is a little bit tangential to the main line of our discussion. What I would like to do is I'd like to evaluate this integral, which was so important in our calculation of the stationary phase equation. So in order to go from our simplification of the stationary phase equation to its final answer, we needed to know how to solve this integral, this Gaussian-like integral. It's actually a Fresnel integral. And I provided you the answer in the last lesson saying, oh, this is a well-known integral, and it is. But the exercise of solving for it develops or reminds us of some complex analysis that is really definitely worth going over. So with that in mind, the purpose of this lesson is simply to derive this final expression, this well-known expression of a Fresnel integral, and it'll involve complex integration, integration of a closed contour on a complex plane, and Jordan's lemma, and a few other really important techniques that are always used, and it serves as a good review of those, a reminder of what they are. If it's the first time you've ever seen any of it, then you really need to sort of stop and study complex variables a little bit, which is no shame in that. That's a fun subject, and I'm jealous. It's like reading a good book for the first time. It's really exciting to learn how complex variables and complex analysis works. So with that in mind, let's begin. So we will begin by noticing that the integral we're interested in is symmetric about 0. So it can be 2 times the integral from 0 to infinity of e to the I alpha z squared dz. I'll remind you it looks like a Gaussian, except a Gaussian requires a negative sign, not an I, right? So we're going to work on this integral, it turns out. Now remember, none of this is anything you'd be expected to do from scratch, but you should be able to follow everything here comfortably, as difficult as it might be. To imagine, difficult as it might be to imagine inventing it. Like I said, we're kind of walking the path of some 19th century mathematician. So this is our integral. This is what we're after. It's a complex integral in the sense that this is cosine alpha z squared plus I sine alpha z squared. And each of those, by the way, are Fresnel integrals, right? So this is a combination of 2 parts. In other words, the real part of this and the complex part of this are the so-called Fresnel integrals. And alpha is a constant, and in our case, it's a real constant. So alpha is a real number. Z squared is a complex variable, right? This is a variable in the complex plane, but 0 to infinity is along the real line. So even though z is a complex variable, we're going to treat it like a complex variable. The integral we're after is a real because the imaginary part of z doesn't participate. However, it's complex in the sense that this I is in there. But the I could be treated as a constant as long as your integration is completely real. But anyway, we're going to look at this as a complex integral, and a complex path integral, I should say, in the complex plane. Now that I've said that in a million confusing ways, if this is the complex plane, and we're going to go from 0 to infinity in the complex plane, that is a contour in the complex plane. So it is a complex interval, despite the fact this particular contour is on the real line, right? Okay, so with that in mind, the first thing we're going to do is we're going to try to actually make it look a little bit more like a Gaussian. So I'm going to introduce a minus sign, and then I'm going to introduce another minus sign, because e to the minus I pi over 2, right, that is minus I. If you don't understand why that is minus I, that's a fundamental gap that you want to fill before moving on into QED or any other sophisticated physics. But e to the minus I pi over 2 is minus I. So given that that's minus I, we have minus I times that minus, and we end up with just the I that we started with, okay? So that's really not even a thing, meaning it's just a pure formal maneuver. But it is important because that formal maneuver allows me to pull out this square or outside of these brackets. So if I pull out the square outside the brackets, I'm left behind e to the minus I pi over 4, square root of a, z, all quantity squared. And now you're beginning to see, right? That looks a lot like a Gaussian. If this, which is a complex number now, right? Because this is cosine pi over 4 plus I sine pi over 4, or actually cosine pi over 4 minus I sine pi over 4. But this up here is a complex number, but it still has this Gaussian structure, right? So not much of a change there. So now what I'm going to say is I want the limit as r goes to infinity, of r, right? I'm going to change that upper limit of integration to a finite number r, and then I'm going to take the limit as r goes to infinity. That's purely the definition of the integral from 0 to infinity, right? There's no such thing really as the integral from 0 to infinity. What you're doing is you're always taking the limit where the upper limit integration is r, and you take whatever the result is, you take that finite definite integral, and then you push r to infinity in a limit. So that's not much of a change at all. But I am going to make this variable, this substitution. I'm going to define u with, that's what these three equal signs mean. It's a definition. U is going to be defined as e to the minus I pi over 4 square root of a z. So all of that in here, that is all going to become u, right? And the limits of integration are really limits on the original variable z, right? That's what these limits are. So I put in these z equals here just to get that straight. I know all that stuff is sort of elementary calculus, but we forget. I mean, I have to remind myself these things every now and then, and certainly I'm sure there are many of you who haven't done it in a while. So after we make that substitution, dz becomes e to the I pi over 4, 1 over the square root of a du, right? So du equals this times dz, and then I have to take this over to the other side, and you end up with e to the I pi over 4 square root of a du replaces dz. In other words, this equals dz. And then, of course, this all becomes u, like I said, and our limits of integration now have to be examined. Not too hard to see when z equals r, right? If z equals r, then u has to equal square root of a e to the minus I pi over 4 times r, because u equals square root of a times e to the minus I pi over 4 times z, right? So the upper limit of integration becomes this kind of interesting complex number. And the implication is that it's a straight line, right? So I go from u, right here, this is the origin of the complex plane, and some distance r, that's e, that is e to the minus I pi over 4 in the direction of e to the minus pi over 4, which is in this direction on the unit circle with length r, square root of a, square root of alpha. But I'm going to take alpha and the square root of alpha, and I'm going to blend it all back into r. So it's just going to be, this length here is just going to be, this length here is just going to be r e to the minus I pi over 4. In other words, I'm just redefining r to be r times the square root of alpha, right? Because it's all a real number, so it's fine. And we're taking the limit as it goes to infinity anyway. So I've got this, so my new contour in the complex plane looks like this, right? The old contour was like that. The old contour is from 0 to infinity. The new contour is from 0 to this point in the fourth quadrant of the complex plane. So now the point is that the original integral I was interested in terms of z, going from 0 to infinity, is now equal to this integral here in terms of u. And this integral is a Gaussian. So we've got this, I guess this is the final answer right here, when I pull out everything. And is there any difference between these two? Oh yeah, the difference between these two is r is no longer r squared alpha, right? That's what I just said earlier. So we've completed that transition. And the benefit is we just got this nice thing that kind of looks like a Gaussian, but still it's a complex interval. It's a contour integration in the complex plane, right? You're going to integrate this integrand along this value of this line. So each of those complex numbers gets put in there. It could be done, but the only benefit is that we've turned it into something that has a Gaussian in the integrand. The problem is it's the Gaussian of a complex number. So how do we get at that? How do we get at the answer? Because remember, we need a number. We need some kind of numerical answer, be it complex or real or whatever it turns out to be. So what we are going to do is we are going to appeal to Cauchy's theorem. And this is just one of several of Cauchy's theorems. But basically, Cauchy's theorem, the one that you need to know. Well, there's three fundamental theorems of integration, I think, that you absolutely have to be comfortable with. Cauchy's theorem is obviously one of them. And it basically says that if you do an integral around any closed contour in the complex plane, right here, so here's the complex plane, here is a closed contour. As long as the function that you're integrating, right, so this would be written down as the integral around a closed contour, you might call the contour gamma, say, of some complex function, right? As long as that function is completely analytic everywhere inside the contour, then this guy is always going to be 0, right? So the things you need to understand here is what is analytic, right? What is an analytic function? And in order to understand an analytic function, you have to understand the idea of poles, right? And the idea of a Taylor versus a Laurent series, right? All of these things are essential complex analysis topics that matter. They're not that tough, by the way, right? The idea of being analytic means that the function has a Taylor series, just a Taylor series inside this region. Some functions are analytic everywhere on the complex plane. For example, the Gaussian function is analytic everywhere on the complex plane. So so if it has a Taylor series, it's analytic. If it doesn't have a Taylor series, then there could be a lot of reasons. One is it could just be a non-analytic function, but an analytic function also has, by virtue of having a Taylor series, it also has a derivative, a logical complex derivative. So I can always write df of z dz everywhere that f of z is analytic. Where f of z is not analytic, it has some kind of pole. And those are captured not in a Taylor series, but in a Laurent series. And a Laurent series is just like a Taylor series, but it includes terms like 1 over x minus a, and then 1 over x minus a squared. I guess I should write b1, b2, right, all the way to, as many as you need, right? Often it terminates, sometimes it doesn't. When it doesn't terminate, you have different kinds of singularities. You have essential singularities if it doesn't terminate, and then you have poles of order 1, poles of order 2, etc. if it does terminate. So there's a lot to know about complex analysis that makes some sense. So the point is that any closed contour, the one that we need to know right now is Cauchy's theorem, that any closed contour of an analytic function in the complex plane, that closed contour is going to give you 0, the integral around that closed contour. Notice the integral around the closed contour, it's not a surface integral the way it might appear because I spent some time filling it in. I filled it in to say the function's analytic in there. The contour is just the integral on this line, right? So the integration is just on this line, right? Now I said there were 3 integration theorems you really need to know well. So this one is Cauchy's theorem. The other integration theorem that's important is also named after Cauchy and is called Cauchy's integral formula, which looks like this. We're not going to need that right now. We will use it later in our discussion of steepest descent, however. But just keep in mind, these two are different. Cauchy's theorem is this idea that this integral around a closed circuit that for which a function is totally analytic is 0. Cauchy's integral formula says the integral of a closed circuit around a point A, right? I guess little a, right? Around a point little a, this line integral totally circulating around a point little a, the line integral of f of z over z minus a, that is the value at f of a, which is kind of remarkable if you think about all the different possible contours you could take around this point a. As long as you put this z of minus a in the denominator of your integrand, you'll get f of a. And then the last of the three big ones is, well, it's probably the biggest one, the residue theorem. And we will be using the residue theorem later, so we'll have a chance to practice with that later. We'll practice with this maybe a little bit in stationary phase, but this one will push off to more of our scattering theory. Anyway, the point is once we have Cauchy's theorem in hand, we are going to find a contour for which our integral is a part of the contour, right? That's this integral here is part of that contour, and we're going to find the rest of the contour such that we can set it's equal to 0, and we can evaluate each leg. And by evaluating each leg, we can find the value of the integral we care about, all right? That's a typical standard trick in this business. Discover a contour that contains your answer plus two things you fully understand, or a couple things you really understand, or however many things you need that you really understand. And use Cauchy's theorem or the residue theorem to set that unique contour to some value. In this case, the value is 0 because we're using Cauchy's theorem, which that's what Cauchy's theorem says. These things are going to be equal to 0. Closed contour of an entire function is going to be 0. An entire function means a function that's analytic in the entire complex plane. Such a function is called entire. Although that is a bit old. That is a bit of old usage, an entire function. So we are seeking this clever contour. And that's where the cleverness comes in, right? That's where the 19th century mathematician's mind comes in, is he gives us these contours, and then we execute the integrations, and we go, man, that was a clever contour. Good job. And then the guy gets the contour named after him, right? So you'll see things like Hankel's contour, right? Because Hankel was the clever guy who figured out the right contour. So we're looking for a contour that's going to help us figure out the value of the integral that we're trying to study. So let's have a look at how this is done. So this is what we've got so far. This is the integral we want, right? We know that this contour is the one that we have decided is equivalent to the actual integral. If we found this number, right? This is a number. It's a definite integral. du is the variable of integration. There's no variables left over. This is a number. If we found this number, we'd be good. And this number is this contour integral in the complex plane, right? Where this is the real axis, this is the imaginary axis. This is mostly the negative imaginary axis. So the contour we're going to use, the clever contour we're going to use, is going to go from 0 to this point, a distance r, e to the minus I pi over 4 away. Of course, ultimately, r gets infinitely big, but we're just going to set it to be finite for right now and then take its limit. Then we're going to take a circular arc back to the real line. We're going to take a circular arc just like this back to the real line. So I guess I'll draw that. A circular arc back to the real line. And then once we've got that, we're going to take a path that goes from where we land on the real line, which is obviously r e to the I 0, right? And we're going to follow that back to the origin, right? And we know that the contour integral along this path is 0. And I'll call this contour here well, let's see, what did I call it? I actually wrote this down. I called it circular arc, right? So this contour will be CA for circular arc. And so we have our integral, right? That this is a stand-in for this thing here, right? That's our integral. The contour integral of our function along the circular arc plus the contour interval from r to 0. The sum of those contours has to equal 0 because those three contours add up to a closed contour in the complex plane of a function, well, I guess of a function up here that is analytic everywhere, has no poles, right? So this here is the integral that we want to do. So I'd love to know the answer to this. The question is if I can calculate the answer to this, and if I can calculate the answer to that, right, then I know that this plus this, whatever that is, must equal this, or the opposite, must equal the opposite of this. Because remember, the total integral has to be 0. So this plus this equals 0. I'm saying that I can maybe calculate these things. And the reason this is a clever contour is because indeed I can calculate these things. I wouldn't have necessarily known, but some 19th century mathematician who was in a pinch figured this out. So we are now going to calculate the integral along this path, and we are going to calculate the integral along this path, and we're going to add those two together, take the opposite, and we're going to call that the answer. Okay? So let's begin by looking at this path. So now if we go back to the integral, this is the integral we were initially interested in. This is obviously along the real line, right? But all of these processes that I did never depended on the actual path, right? Doing this change and then doing this change and then making this substitution. None of that really mattered. The place where it really mattered is when I fixed and adjusted the limits of integration based on the substitution. I had to sort of use the 0 and infinity for the dz and change it to u. So for any path integral that I do, I can use this calculation, except I have to have the correct limits, right? And that's exactly what I'm going to do. The path along the circular arc, it's the same Gaussian that we landed with here, right? Except in this case, I'm going to go ahead and call it the complex variable z. And I just have to make sure I get my limits of integration right. The bottom limit is the last point of the first contour, which is r e to the minus I theta. So this point is the beginning of the contour. The end of the contour is just r e to the I 0, right? But the path is a circle. So when I write down the integral, I can show the endpoints, but there's nothing about the nomenclature of this integral that really describes the path. In fact, this almost looks like a real definite integral of some kind, even though you have these complex numbers. You know something's up because the limits of integration are complex. So the first question is, well, what's the path of integration, right? Now, there's another important principle that the path of integration of a function, of an analytic function in the complex plane doesn't matter and can be deformed as long as you don't pass through as long as the deformation doesn't pass through any singularities, right? But we do want it, but not every path can be calculated. They may all be equal, but they can't all be calculated. So we want to find a path that we can calculate. And it turns out this circular path, we've chosen the circular path because we can calculate it. So there's nothing here to represent that this is a circular path. So you might put something down here and say, you know, the path CA, right? And you know, strictly speaking, this path CA is very well identified that it starts here and ends there. So these two might even be redundant if you put the path CA there. But anyway, I'm just marking the endpoints, but it's along this circular arc. So now what enforces the circular arc, right? So Z is just an arbitrary complex variable that I'm saying is along a circular arc. Why don't I make it so I can actually do it? And whenever you're moving in circles, the common maneuver in complex analysis is to replace your complex variable with r e to the I theta. Put it in its polar form, right? Every complex number z can always be written in some form, e to r e to the I theta, right? This is the polar form of a complex number. So let's just write it in polar form. So if I say z equals r e to the I theta, everywhere I say z, I replace it with r e to the I theta. And dz, of course, if I'm going to replace the differential, is going to be r e to the I theta d theta, but that d theta is going to pull out, the differentiation is going to pull out an I. And that's where this piece comes from. So this here is d theta, and this is just z. I'm sorry. This piece here is dz, and this piece here, this r e to the I theta, is z. All right? There, I cleaned it up a little bit. So after making those substitutions, this is now, we're working on that second leg of the contour. I just make a few changes. Let's see, I note that, here's an interesting problem. The variable of integration here, these limits are written in terms of z, right? So I should have written, equals z there. And the next step is I convert those to theta, right? It's now an integral in terms of theta, so I just have to go from minus pi over 4 to 0 in terms of theta. IR, that part from the IR part from here just comes right out in front because it's a constant, right? And let's see, the e to the I theta has to stay behind because theta is the variable of integration. And that's all the changes for that segment. Then to go from this, that expression, the expression we just completed, to this new expression, I just blowed up. I just blowed up the this exponent, so I get r squared e to the 2I theta e to the I theta d theta. So this is now the integral we're working on to calculate. And it's something we can do, right? Now, d theta, this is a real integral, practically. I mean, there's a little I in there, but the integration, this is a straight integration, if I could do it. I just treat I like a constant. This is basically a real interval. But the question is can we do this integral? And the answer is, in complex analysis, you don't always have to execute the integration. You don't have to put it into a form you can literally do. What we're going to show is that the integral along the circular arc is actually 0, right? That's the beauty, is the guy who did this figured out that integration would be 0 as r goes to infinity. And so I take this expression, and I'm going to prove that it ultimately, as r goes to infinity, it's 0. Or the magnitude of it is 0, right? So I take the magnitude of that integral, and I'm going to show that that's, first of all, that's less than all of these magnitudes broken up, right? That's just a principle of magnitudes. So the magnitude of I is just going to be 1, so that's an easy one to figure out. R is a positive number, so I don't even have to put magnitude signs around that. The magnitude of R is R. Then the magnitude of a product is the product of its magnitude. So I do have the question of what is the magnitude of this thing? I have e to the I theta, but that's always on the unit circle, right? Whenever you see e to the I something, and that something is real, theta has to be real, right? That magnitude is easy. That's going to be 1. So this whole thing is less than this integral of this magnitude. So I have to work on what is this magnitude, right? What is the magnitude of e to the minus r squared 2I pi? And the process is actually oddly easy from this point. Well, the next few steps are easy, right? I substitute Euler's expression for e to the 2 pi I. I blow that up as cosine 2 theta plus I sine 2 theta. And that breaks this thing up into a real part and an e to an imaginary part. And the e to the imaginary part is 1, so that goes away. So I know that this integral here, the integral of that magnitude, just equals the integral of this magnitude, of the magnitude without the complex piece. So we're really tightening this up, right? We're tightening it up so that we need to understand less and less and less, because whatever we've got here is definitely bigger than the integral we would need to calculate for the circular arc. But I'm going to show you that even though it's bigger, it still goes to zero. And something that's always bigger than your thing that goes to zero, by the squeeze theorem, it's going to force your thing to zero, right? Because it's the magnitude of your thing that we care about. In other words, we care about if the magnitude of this equals this, and the magnitude of this is always positive, and it's always less than the magnitude of something else, in particular, the magnitude of what I'm circling right now, this integral. So I have the magnitude of this integral is bigger than the magnitude of this integral. Then if I can show that the magnitude of the larger integral goes to zero, then you know that the magnitude of the smaller one goes to zero. And that's the whole point of this. So now, how do we get at this thing? Well, first of all, I can get rid of the magnitude signs because r squared is always positive. And cosine of 2 theta is not always positive, but it is always positive on the range of minus pi over 4 to 0. So because of that, I can get rid of the magnitude signs. And so we do that. We get rid of these magnitude signs. And then we pull sort of a legendary trick in complex analysis. And this legendary trick is called Jordan's lemma. Jordan's lemma. And this is a thing that when you study complex analysis, you learn at some point. You have to. I mean, you can't. It's a lot of proofs just like this one that you can't do without Jordan's lemma. And Jordan's lemma basically allows you to take certain trigonometric functions and make them larger than certain linear functions, right? And it pops up all the time, but it turns out that cosine of 2 theta, cosine of 2 theta, let me put it in green, cosine of 2 theta is always larger than 1 plus 4 over pi times theta. And that's essentially saying something like this, which really isn't all that hard to see. But if this is cosine of 2 theta, right, it's, see, minus pi over 2, pi over 4 times 2 is minus pi over 2. Cosine of that is 0. Cosine of 2 times 0 is 0, so that's cosine. And this line here is given by 1 plus pi, 1 plus, 1 plus 4 over pi. Let's see, what's the slope of that? Yeah, 1 plus 4 over pi theta. So the line is 1 plus 4 over pi theta. This guy here is cosine of 2 theta. And clearly, the line is always less than the cosine, right? So we can replace the cosine of 2 theta. We can replace this because, remember, this is the negative exponent of positive quantities. So the larger this positive quantity is, the smaller that exponent is going to be. So e to the minus r squared of cosine 2 theta will always be smaller than e to the r squared 1 plus 4 over pi theta. So this inequality is totally legitimate, right? Now it puts the proof in a little bit more desperate straits, right? Because I'm constantly bounding things by bigger and bigger numbers, right? So now, you know, at one point I had to prove that this guy was screaming towards 0 as r goes to infinity. Now I've got to prove that this guy is screaming towards 0 as r goes to infinity, but this guy's bigger, right? But that's okay because it turns out it still screams to 0. So that just shows you how much headroom we have in this proof, right? So now we just expand this and I pull out the e to the minus r squared over 1 because that is not theta dependent, so that comes out front. And then I have this integral left. Notice this is an entirely real integral that we can actually do. So we finally have landed at an integral that we can actually execute, right? So let's do it. So this integral here, right, executing this integral in green gives us this result here, right, which is just, you know, the integral of e to the minus a theta is 1 over minus a e to the minus a theta, right? Which is what we're doing right here. And the limits of integration are 0 to minus 4 pi, and then this is the constant, right? The constant that was out in front, that I'm circling in red, is still present with us. And then the next steps are just sort of rounding it out, right? I mean, this is just blowing up the limits of integration, and then I think, what do I do next? I simplify it a little bit, and what's pretty clear is that the magnitude of the circular arc is less than our final result. But as r goes to infinity, this term screams to 0, and this term marches straight to 0. So this magnitude of the integration on the circular arc is 0. And the trickiest part was applying Jordan's lemma, but regardless, we now know that this integral, as r goes to infinity, the value of the contour along this integral goes to 0. So now because of that, we can go back to this expression, right? Our total contour interval is the integral we're interested in, plus this circular arc, plus r to 0 equals 0. I can now say, okay, this guy goes away. Well, I guess I can say that the integral from 0 to r, right, because we put this on the other side, pull in a negative sign, and get rid of the negative sign by flipping the limits of integration. This integral here is now equal to our integral, and the circular arc is 0. So now if I can calculate this integral, then I get our answer. Phew. So let's see what the next step is to do that part. Oh, by the way, this notion of a lemma, right? A lemma it's interesting because this little demonstration here in and of itself is not very important, but you have to take note of it in order to execute this proof. So this is an example of a small fact that you need to demonstrate in order to make a proof go forward. And that's what a lemma usually means to mathematicians. Some lemmas turn out to be more important than others. Jordan's lemma is used quite a bit, so it gets us, it's a name that floats out of the very proof that it's used in. It's used in, like, for example, we just used it here, but it was used in other proofs that are very important in complex analysis. So despite the fact that a lemma is usually a very important step of a proof that has to be proven itself, some lemmas pop out and become famous, and Jordan's lemma is sort of one of those. Okay, so what have we shown? We've shown that the integral that we're interested in equals this integral, the integral from 0 to r of our Gaussian along U. And notice, this is a real integral, right? Wow. So again, now that we've got a piece of that integral on the real line that we can actually do, right? Because this is now 0 to r, the limit as r goes to infinity, this is just half a Gaussian, right? And, we've already done this analysis earlier to change this integral into an integral in terms of U. U would normally be a complex number, but this particular contour is on the real axis. So this becomes a real integral. That was the whole point of choosing this contour, is this, although it's a real contour, it's a contour in the complex plane, it's exactly equal to a real integration of a function we can actually do. So this is the integral we don't know. We figured this one is 0, and this one we can do. Ergo, because when you add them up, they're 0, you've got your answer. And that's exactly what we do. This integral here must equal this value right here. And this guy, we know, right? We know the answer to this in the limit as r goes to infinity of that integral is going to be the square root of pi over 2, right? If it was minus r to r, then it would be the square root of pi, right? But it's half of that because it's symmetric. So we end up with this expression, right? So the integral that we were seeking, this thing, is e to the I pi over 4 times 1/2 times pi over, times the root square root of pi over alpha. And ultimately, if we go way back to the beginning, we remember that this guy was 1/2 of the integral we were really seeking, which was the integral from minus infinity to infinity e to the I alpha z squared dz. So we now need to multiply this creature down here by 2, right? And we get our final answer. I guess I didn't have to drag it all the way up there. I wrote it down right here. So this was a demonstration of how you would use Cauchy's theorem. And it's an important thing to understand, and it's a really great application. This, remember this, the reason we went through all this trouble was because back here, when we calculated our integral for the stationary phase approximation, it showed up right there, right, with x phi prime prime over 2 being a, right? So this part here was our alpha, right? That was alpha. And we needed to know this in order to get our asymptotic. So it was actually a very important piece of our work. And here's where that phase shows up, right? That phase shows up right here in our final result. And remember, our sines and cosines back in our Hankel expressions, right? Look, all of these guys, you see these phases up there. And there's pi over 2, pi over 2. You can almost feel where these phases come from with these asymptotic methods, right? We've got a pi over 2, right? Or we found an e to the I pi over 4 right from this integral, and then it's showing up in the phase here, right? So somehow between this exercise and our spherical Bessel function's steepest descent that we're going to do in the next lesson, somehow that becomes a pi over 2 with a factor of L. Okay, so that was a little sort of supplementary lesson just to exercise some complex analysis. Our next lesson will use the method of steepest descent. You're going to see that analysis go forward, and here we do a completely complex problem, meaning an integral representation entirely in the complex plane using a complex variable, but it's still of a real variable x, right? That asymptotically x goes to infinity and x is real, but everything else in this integral representation is complex. And you'll see we just sort of proceed much the same way, but it's much harder to figure out how to get this final integral to be useful to us, right? But nevertheless, and it's very heavy in complex analysis, but we're going to do it, and that'll be our next lesson.